Hello, everyone. Thank you so much for joining me today. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging, and I'm excited today to be able to help you if you're struggling with your tight treatment fields, talk to you about small field detectors and in particular, of course, our W2 scintillator. See if my page will advance here. A little bit of housekeeping before I get started. We are recording the webinar today. If you have questions, feel free to enter them at any time in the GoToMeeting dialog box. I'll try and address those as they come up. If I don't get to them, or if you think of something later on, we'll certainly circle back around to those at the end of the presentation. If you don't know much about us, Standard Imaging is based in Middleton, Wisconsin, just outside the capital city of Madison. Have a beautiful campus right there, but of course, these days it looks a little bit frostier. Still fun though. It was founded in 1989 with a modest selection of products, but has grown significantly since then, and we now design and manufacture a full suite of QA products for radiation therapy. So into small fields. To put things in context, I like to start with what really qualifies as a small field. So the joint publication from the IAEA and the APM, Technical Report Series 483, I'm sure most of you have taken a look at this if you're already struggling with small fields, but it has a definition of small fields have at least one of these conditions, either loss of lateral charge particle equilibrium on the beam axis, partial occlusion or of the primary photon source because you've collimated so much, down to such small field sizes, or the size of your detector is similar to or large compared to your beam dimensions, because that takes us outside of the assumptions that we make for cavity theory and things like that. So then once we've got our definition, it really behooves us to take a look at how our choice of detectors really impact the measurements for these small fields. First and foremost, of course, is your detector size. I like this image from Meltzner and DeWord from a few years ago. They were looking at gamma knife helmets and showing just the size of the ion chamber they were using. Expected some volume averaging to occur with this 4mm helmet, but what came out of the publication is that the extent of actually the buildup around that active portion of the ion chamber also meant that the 8mm helmet was affected with some volume averaging. So it's important to think of not just how big is my air cavity, but how does that really impact this equilibrium off to the side with the full size of my detector and the shape of my detector. The profile, as we were looking at in that plot, relative to the chamber's spot size, which is a metric that we like to use just to describe that physical shape, physical extent of your detector. And if you've got a spherical spot size versus an elongated spot size, then of course the orientation of your detector within your field plays a role as well, especially in determining your beam penumbra accurately. So consistent and accurate positioning also matters more as your detector size becomes comparable to the size of the field that you're measuring. Second point would be perturbation of the beam. What sort of materials are you putting into the field right there at the point of measurement? Perturbing the fluence of the beam itself, you're really altering your dose just because of the fact that you're replacing water with your detector. And I know everyone really knows this, but it's good to refresh ourselves once in a while. So when you're looking at detectors and considering the perturbation, really there are several questions you should ask yourself. With an ion chamber, you look at how big is that air cavity compared to the fields that I'm measuring. For a diode, it's really the density. We're looking at a higher density material with diodes. Some of them have built-in compensation, which is a lower density area right next to the high density portion in an effort to try and balance the energy dependency, the interactions of the field there. Scintillators, actually I should, with diodes as well, you're looking at how that response varies with energy. And then for scintillators is the material. Not all scintillators are created equal either. Is the material that's used in the scintillator and in any optical transfer fiber that's being used, is that really water equivalent for the beams that I'm interested in? There are often published corrections available for a lot of the detectors that we're using, but one thing to be aware of as you're trying to account for these perturbations is that if possible, you really need to be matching the published conditions in order for the correction really to apply, or be aware of those deviations and potential impact on your measurements. This is just an example of one of the publications from Paulo Francescon, looking at detectors that over-respond. So we're looking at corrections below 1. These are all the diodes, stereotactic diodes that they investigated, as well as our scintillator, the W1 at the time. And then the ion chambers, so corrections greater than 1, just as an example here. So third question, what's our signal level? Is your signal, for the ion chambers, your signal is proportional to your collecting volume. So a smaller collecting volume gets you a proportionally smaller signal. And as your signal decreases, your signal to noise ratio becomes more of a concern. And your small signals require an electrometer that has the appropriate sensitivity and noise floor in order to measure those quantities accurately. For a diode, you get a nicely larger signal than from a micro-ionization chamber, but of course, as we've seen, there are some trade-offs there as well. With a scintillator, the smaller you make the scintillator, the smaller your signal level gets, just like an ion chamber. It's a geometric factor there. So a very small scintillator gets you a small signal level, which means if you're scanning with it, you have to do some slower scans. Signal to noise ratio, of course, is related to that. You need to give your electrometer proper warm-up, evaluate the leakage so that you know how big an impact that might be having. If you have leakage on your electrometer, matching ranges, of course, and then being aware of the cables that you're using. As we get down to these really small signal measurements, the cable actually can play a much larger role. If you have a really long cable that you have recently unwound, it takes a while for just physical effects, that cable to relax, and that can cause some triboelectric type current. Very small, but can affect your measurements for those small fields. Accuracy of your detector. How accurate do you need it to be? What plays into that, particularly energy dependence? Diodes can occasionally have low response out of field in those scatter regions, which can lead to an underestimation of the low dose region in your SRS patients. Again, there's that question of whether the diode is compensated or not. How does that play in? Is this appropriate for what you're doing with it, or is it maybe bringing in some additional perturbation in that way that might not be what you're looking for these measurements? If you have energy dependencies and you're measuring depth doses, then your corrections become depth dependent as well, because your energy is changing as the beam is being attenuated. And change in scatter conditions, especially for something that has a high energy dependence on the low energy end of the spectrum, can affect your responses. Not quite as prevalent or as tricky to deal with, I guess. There's angular dependencies. Generally, just using the detector in the orientation that was designed for is the best bet there. But be aware there may be some implications of using things off-label, as it were, at a different angle than designed for. Dose rate and dose per pulse dependencies, especially with flash becoming an interesting topic, then those have been brought to the forefront a little bit more lately. But it does affect the standard linear accelerator measurements as well. It requires an understanding, of course, of both your accelerator, how it produces those higher dose rates. Is it just more pulses, or is it higher pulses? And your detector, what sort of dependency does it have? So what's the physicist to do? I'm trying to fly through that overview. I know you guys want to get into more of the detectors, the W2 in particular. But pause, take a deep breath. There's a lot to think about there. And I'd like to offer least a handful of solutions to help you get started on your way. First, of course, is the ionization chamber. Our Exradin A26 is the smallest reference class ionization chamber that we make. The A26 is smaller, but there are slight differences there. The diode is the D1V. It's a very nice scanning diode for stereotactic use, actually general use as well. And then the detector of the day, I guess, the W2. I'll be honest, every detector that you will come across has both strengths and limitations. I will try and present these because I believe in being open about and bringing that education to you guys so that you can make a well-informed decision. And really the best solution, and you'll hear this from other people as well, the best solution that you'll find is a good combination of detectors so that those strengths and weaknesses, well, the strengths of one can kind of compensate for the weaknesses of another detector, as well as building your confidence in your measurements. So the A26, just a kind of brief highlights on this one, was designed in response to observation of poor behavior from microchambers across the board from all manufacturers, especially when it came to ion recombination and polarity type effects. And so we're happy to say that this one really is a reference class type chamber, behaves very well. We were able to get it to a spherical spot size so that your angular orientation it doesn't matter. It is independent of that. We modeled the electric fields really to be sure that that shape was what we expected it to be, not just counting on the machining itself. The chamber volume for the A26 is an order of magnitude lower than our scanning chamber, the A28, so a nice small volume there. But if you compare, the A16 is our smallest chamber. It is twice as large in terms of volume as the A26, but in terms of spot size, you're less than a millimeter larger on the actual physical dimensions of the chamber. So you get a good signal, a little stronger than the A16 without compromising very much at all on your spot size. So strengths of the ionization chamber, the A26 in particular, it is a reference class ionization chamber. You can expect very stable and predictable behavior from it. That spot size is independent of the beam orientation. And ion chambers really are familiar technology for most of us. This is something that we've worked with all along. We're comfortable with troubleshooting when things start to go wrong or look funny. We recognize when things look funny. Limitations are size. You can only make an ion chamber so small. There is still a small perturbation of the beam due to the air volume in there. With our diode, we do have two orientations. I like to talk about the D1V, that's the scanning diode here, that's the vertical orientation, but there is a horizontal orientation that's designed for slab phantoms, a little easier to mill those channels. Or align to the surface or something like that. But they're the same diode inside the housing. It's an unshielded diode with a 1 millimeter diameter spot size. There are correction factors available from publications like from Papakonstantopoulos down here that I've grabbed this plot. There are two publications. This is one of them, of course, in 2014 that looked at both the measured and the calculated factors for that. So there's some reassurance there that it's been looked at. This is one of the other publications, same plot I showed earlier, but if you'll note that the D1V here is the least amount of corrections required for all of the stereotactic diodes that were investigated by Paula Franciscan. It is well-established technology. We're also comfortable with diodes. We've used them quite a bit. That has minimal volume averaging just because of that small spot size. So you get good resolution on your scans and low angular dependence, which is nice for a diode. Limitations is that it's a diode. It's not water equivalent. So there are some corrections that do need to be applied still. So on to the scintillator, the meat of what you hopefully you're here to hear about. But the Exradin scintillators, we have the first generation version was the W1, and the updated, more recent version is called the W2. But we have, with those scintillators, the fiber construction is exactly the same. The W1 was a 1 millimeter diameter, 3 millimeter long active organic scintillator. The W2 fibers come in two flavors, both a 1x3 matching that W1 configuration, and a 1 millimeter by 1 millimeter diameter, or 1 millimeter diameter by 1 millimeter long scintillator as well. This organic material is water equivalent for megavoltage photons and electrons, and I'll have some data to support that here in just a moment. But that's very, very nice in terms of these measurements of small fields, because you're no longer having to worry about how the spectrum is changing as your field size is getting collimated down, or as you're moving from penumbra to in-field. Those sorts of questions get a lot simpler with a detector that really is fully water equivalent in this energy range. The downside of scintillators is that you do have to correct for the Cherenkov effect. So when you irradiate these optical transfer fibers, you create Cherenkov light, just like that characteristic blue glow in the cooling tanks of the nuclear reactor. And that's a contaminant signal when we're looking at the signal from the scintillator also being optical wavelengths. So we do have a correction method for that. I'll get into that as well. And then these are not absolute dosimeters in the terms that you could send it into the calibration lab for NIST traceability. You would have to do a daisy chain, essentially, a dose calibration against your own detector, and then periodically recalibrate it as the plastics receive dose. There is some discoloration that happens with these clear plastics, particularly this PMMA optical transfer fiber starts to yellow with age. And so eventually that does decrease the signal that you measured. It can change the spectrum that you're measuring just a little bit, and you would need to recalibrate or replace the fiber, ultimately replace the fiber. That would be further down the road. So in terms of water equivalence, that publication from TRS 483 has the W1 listed in its table of detectors. And the thing that I like about this particular publication is every table that the W1 shows up in, it's got factors of unity for the correction factor across the board to the smallest field size that's there. Some of these others don't show values where the uncertainty was too high, and the authors really felt that it was inappropriate to use the detector for those size fields. But nothing else in this publication it is fully water equivalent. So our Cherenkov correction, we use a 2-channel chromatic correction. It's based on a publication from Matthew Guyot et al. From 2011. And what they did is they looked at splitting the full measured signal into two portions. We have a blue scintillator, so that would be this lower curve here that would be the typical signal from our scintillator. Cherenkov signal is a broad spectrum light. And so what's measured is a combination, of course, of these two. But if we divide this into a blue portion and a green portion of the spectrum, we can do a set of characterization measurements where we call it, we deliver dose to that scintillation portion, or the active scintillator, and keep that dose the same, but change the amount of optical fiber that's in the field. So we call these minimum fiber and maximum fiber configurations. Minimum fiber would have the fiber coming straight out of the field, where the maximum fiber configuration wraps it around. We calculate what's called a Cherenkov light ratio by the difference in the signal between these two configurations, with only that Cherenkov component changing. And with that CLR value, then we can correct subsequent measurements of an arbitrary field by using the amount of signal in the green field to correct for the Cherenkov in the blue channel. So that's what's described here in the Guyot publication. In addition to this particular characterization set of measurements, you can do a dose calibration where you give it a known dose in a reference field size, and really that just becomes a scaling factor unit conversion correction to this equation. So with the W2, that's the one that has that is capable of being used more easily in a water tank scanning system. It has dedicated electronics, so the Max SD is our electrometer that's used solely with the W2 fibers. It only takes an optical fiber signal as input, but it has the smarts here to be able to process that signal to once you've saved your characterization values, it will do that correction factor or it will apply the correction factors to your measurements to give you just the dose measured by the scintillation, the active scintillator at the end of the fiber. You can perform point dose measurements directly with the Max SD. You don't need another electrometer to use with that. Or you can actually attach the output of the Max SD to the input of your water tank and use it for scanning. So the Max SD will do a Cherenkov correction for every 10 millisecond integration that it collects from the fiber, convert that into an analog output and output that to your scanning tank. So what that looks like is you put the fiber here. We have an adapter sleeve so that it can be used in a standard chamber holder with anybody's water tank, not just ours, but this is our DoseView 3D tank. The fiber then comes off the back of the outside the water tank, would be plugged into the Max SD. Output of the Max SD goes straight into your water tank scanning electrometer, and you collect data just as you would with any other detector. And then here, I guess, images again of if you're doing your characterization, you do your minimum fiber this way, maximum fiber that way. You only have to do that once before you start your measurements. You don't have to do that every time you measure, but you do want to go back periodically and revisit that just to make sure that as you're using the fiber, as that fiber is aging, that nothing's changing or changing too drastically with your CLR or your dose conversion. So strengths of the scintillators of the W2 in particular, actually this is for both. Our scintillators are water equivalent for MV photons and electrons as exhibited by that KQ value of unity in TRS 483. We're not observing dose rate or energy dependencies with these. There is a negligible temperature dependence at room temperature measurements. If someday we were to go to patient surface measurements or something like that, which we're not FDA cleared for, but that temperature differential between body temperature and room temperature might require a temperature correction unless you calibrate and do your characterization at body temperature instead. For QA measurements, though, that's not important. I guess I can give the value. It's about 0.1% per degree Celsius is the temperature dependence. There's you can have them with a very small spot size with that 1 by 1 millimeter active region. They're also MR compatible. The Max SD would have to stay outside the 5 Gauss field line for your MR Linac, but the fiber itself has no metallic parts, so it's can easily be used for measurements inside the MR Linac. Limitations of the scintillator: you do have to recalibrate them occasionally. Optical signal measurements are actually a little bit non-intuitive to many users. We're used to our ion chambers, we're used to our diodes. Troubleshooting when something seems a little funny with the scintillator is a little tougher until you really become comfortable with the behavior of the scintillator and come to an understanding of how things are working there. The other limitation is just kind of an inconvenience on this one. Because it has a low signal to noise ratio, you have to scan somewhat slowly in order to decrease the noise in your scanning. But we're talking small fields, and it is completely worthwhile. And everyone I've talked to about it has agreed it's totally worthwhile to take that little bit of extra time to scan those small fields a little slower in order to get good data that you actually trust. So here's one example of a publication from Paulina Galavis where they compared when the W2 was first being released. There was some concern about whether how well it matched with W1. characterization, which it's the same fiber. We're not surprised that it matched fine. But they also looked at how it performed in a scan. And this is a 1 by 1 centimeter field looking at radiochromic film in the blue dots compared to the W2 with the red stars, and it overlaid beautifully. So with that, I would happily circle around to questions. I really appreciate your attention. I know I tend to talk fast when I'm flying through some of these, so please slow me down, ask me something. There's a question about the yellowing of the plastic fiber. How can it be mitigated? It really can't. It's just something that you have to be aware of. The more dose you give the fiber, the more it turns yellow. I think we've all seen really old PMMA plastic phantoms, or slabs that have yellowed with age. You lose. Oh, now I'm going to forget the numbers. I think it's 2% signal magnitude for about every kilogray of dose that's delivered. So it is a relatively slow degradation, but it does happen. Another question, what is the W3 and how does it differ from the W2? We don't have a W3 yet. So if you have suggestions of what you'd like it to be, definitely reach out. But the W1 is just the fiber and the optics. You need to use a 2-channel electrometer in order to do that Cherenkov subtraction. Our Supermax electrometer has a wizard built in to help you with that. But there's also an increased electronic noise floor that affects the lowest dose rates that you can measure with the W1, simply because the optics and the electronics for the signal processing are not integrated. There's noise that comes from additional connectors, additional cables that go in between. The W1 also, at the moment, if you need to replace your fiber, you need to send it to standard imaging because it's fixed to those optics, where the Max SD is a user replaceable fiber. So if you accidentally, your resident runs the cart over the top of the fiber and breaks it or kinks it or whatever that happens to be, or you've just used it enough, you need a new one, you can certainly purchase a new fiber from us. And the last question, unfortunately, I didn't answer before the person who asked it has left the webinar. Asked if we were recording, and yes, we are recording, so we will send that out. Watch your email in the next few days for a link to the recording. So you can share that. You can review later. You can go back and slow me down at your own leisure. Yes, you will see a recording. Is the W2 available in Europe? Yes, absolutely. If you have questions about whether you about getting that, please reach out, and we'll connect you with either the local distributor so you can get it more easily that way, or with a sales representative here. So thank you so much. I don't see other questions at the moment, but feel free to follow up with us afterwards. There is more information on the website at standardimaging.com, or you can always reach out to us via the sales contact, sales@standardimaging.com. So thank you so much, everyone, for your time. Have a wonderful day.